So does anybody have questions about the homework? No, it's pretty straightforward. I think I got, somebody emailed me and was that somebody from this class who emailed me about a question there?
Yeah, that was me.
Okay, I hope I answered. Let me get the lights. Anything? All right, well, we went through, if you're ready to go, we went through normal incidents. It means a wave that's coming and hitting a surface right, at 90 degrees, or the direction of propagation is right into the surface. The next thing we talk about is oblique incidents, and I'll just tell you where we are in the text. If you've got your text, and I recommend you do take it.
359.
Pardon?
I think it's 359.
Yeah. 359 would be the actual beginnings of oblique incidents. And I'm going to just try to make this easy to understand. And hopefully it won't be very difficult for you to get this laid out. All right. We talk about oblique incidents. What we're talking about is this. When we have some media 1 and some media 2, this is typically air, typically, and this is something else. This media has some intrinsic impedance in region 1, and it has a beta in region 1. This has an eta 2 and a beta 2. Here we're going to do the case of the lossless media. And we're going to have a wave. Now, we'll call this the z-axis. This is going to be consistent with Dr. Wentworth's book. This is going to be x, and then the y-axis is out of the board. You can all see what I'm doing here. All right, so oblique incidence is this. The wave is going to come in, but it's not going to come in at this angle. It's going to come in at some angle that's between 0 and 90. And this is considered the angle of incidence. The actual wave is traveling in this direction. And the first type of wave we're going to talk about is called a transverse electric field, or TE, transverse electric. Now, what does it mean? Well, transverse electric means that the electric field itself is pointing out of the board. So I'm putting a little dot with a circle around it to indicate that the field's coming out. Are you all with me now? The way that I was told this when I was sitting where you were is, if you look at an arrow coming at you, you see the tip and something around it. If it goes and penetrates, then you're looking at it, or it's pointing the other way, and then you see feathers. That's basically, if it's going the other way, it would have feathers, but that's, or just a cross like that. So the electric field's that way, and I know that E crossed H is the direction of propagation, so the H field will be this way. Y'all follow me on this? Now, we're going to write a mathematical expression for this. So as this wave's coming in, obviously it's not coming in where the angle is 0 degrees. That would be normal incidence. It's coming in at some angle, at least we're going to assume, between 0 and 90. And it will lead to a wave that's transmitted So this will be theta transmitted, and it'll have an electric field also. The electric field will be in the same direction, will be coming out, and I'll have a magnetic field also, and H transmitted here. And the H transmitted is going to be perpendicular like that, and this is the direction it's propagating. And it will also have a reflected wave. And oh, by the way, I didn't put this down. That's the angle. That's the angle of transmission. This will be the angle of reflection. Something I'm going to tell you. How many of you have played pool or billiards in your life? All right. Billiards is something that's useful. When you actually make a bank shot, you notice the angle it hits, unless you put a heck of a lot of English on, is the angle it comes off at. All right. Well, in electromagnetic scattering, the angle that this wave hits will be the angle it is reflected. We can prove that, but I'm going to give you a spoiler. All right. It's true. Now, to calculate the angle of transmission takes a little time, but so this is going to be the direction of propagation of the reflected field. And I'll put it here. We have some E reflected, right? And then E cross H has got to be the direction. So that means the H field reflected would be in that direction. Okay, so these are the standards. This is going to be the the coordinate system I used. That's going to be Z, X, and Y. It's a right-hand coordinate system, so if you have a right hand, then you put your thumb in the direction of X and cross it into Y. Or, I'm sorry, put your index finger in the direction of X and cross it into Y. It points in the Z direction. It's a right-handed system. A left-handed system would have the opposite. All right, but everything we do to be consistent so everything works right, we do in the right-handed coordinate system. So how do we mathematically describe this right here? Well, the way Dr. Wentworth chooses, and a lot of other people have a similar way, they're going to say the incident electric field first is going to have a magnitude, E naught incident. Then it's going to be directed in e to the minus j beta 1. And here's where it gets a little interesting. Now, up here, we're going to have beta 1, and it's going to be x times the sine of the incident angle plus z times the cosine of the incident angle, and it will be in the AY direction, or sticking out of the board. So here's something different. I have the x and z times the sine and the cosine. So why do I do that? Let me show you the reason. In general, even though Dr. Wentworth's book doesn't talk about this, when you talk about a wave moving through space or anything like that, you're taking a look at something, and you'll be taking a look at the way they normally do it. They don't even use beta, they use K. It's a common symbol in physics and in electrical engineering for wave number. K is the same thing as beta. Let me just digress for a second. So K is equivalent to beta, all right? But K will always have a vector sense. So K will be a vector. Now, what is this actually? The magnitude of K is this. K is equal to, in our case, omega square root of mu epsilon. So it is just like the wave number if we're talking about a scalar vector, all right? In terms of its magnitude. But K itself has some Kx, Ax plus some, in general, there's three components. K, in our case, Kz, Az. These are the weights in the relative direction it's going. Let me explain for a second. Kx here will be equal to K, that's just beta, or the magnitude. Then it would be times the sine of theta incidence, Ax, and this would be Ax, plus magnitude of K, and it would be times the sine of, cosine, not sine, cosine of theta incidence, Az. Now, think of K like a weight times the direction of propagation. Can you all imagine that? So if it's coming normally incident here, K would just be omega square root of mu epsilon, or just beta, right? And it would be in the AZ direction. Well, what would the angle theta I be at that point? Theta I would be 0, wouldn't it? And if you look at this, the sine would be 0, so it has no component in the direction of x, and the cosine would be 1, so all of it's in AZ, and it makes absolutely perfect sense. So this is the way we give a directional sense to electromagnetic propagation. They'll put a k vector there. K has to do with the wavelengths and a certain, k is really 2 pi. I mean, beta is 2 pi over lambda, lambda is 2 pi over beta. Think of it that way. And without getting into too much more detail, the larger the value of k is, the smaller the value of beta is. And it's very useful for understanding how waves, what direction waves are traveling. So if we think of a wave traveling this way, right, where we have a wave traveling this way, here's my k vector. Well, that actually would have a kz and a kx component. Does this make sense to everybody? Now, what is kz? It's just the projection, or it's magnitude of k times the cosine, and you'll see right here. That makes perfect sense. Magnitude of k times the cosine times AZ is a projection in the z direction. Magnitude of k times sine of the incident angle is the magnitude of k in the x direction. Y'all with me on this? And that's exactly what Dr. Went was showing you there, only in a slightly different form that doesn't really bring out the fact that there is a k vector this in the direction x and a k vector in the direction z. All right, that's because that's the way the wave's propagating. It's propagating in both the x and z, but not y. Y'all follow me? This will come in useful later. I'm going to erase that. That's not in this book, but it's very useful because if you're looking online, you're going to see people referencing that all the time. K and beta are interchangeable. Anyway, that's his incident field. How would I get the magnetic field? These are assumed incident magnetic field. I didn't say this, but this is all for plane waves. So if we have plane waves, we know that they're a long way from the source. They basically are like waves on an ocean surface if you're a long way from the source of the wave in terms of its analogous behavior. And we also know one other thing. This is valuable to remember. To get H, I can take 1 over eta 1. That would be the eta, the intrinsic impedance in media 1. And then I could take a unit vector in the direction of propagation, crossed it in to the E field, incident E field. Do y'all remember that? All right, those are things you kind of need to remember. Well, a unit vector in the direction of propagation, I can get fairly easily. There's a lot of ways, but I'll just tell you the easiest. If I want a unit vector in the direction of propagation, I simply take kx ax plus ky ay over the magnitude of k, and that'll be a unit vector in the direction of propagation. So what is it really? Well, that's simply going to be sine of theta incident ax plus cosine of theta incident az. And that would be the unit vector in the direction of propagation. Now, the unit vector has one important quality. Its magnitude, actually. Its magnitude is 1, right? If you want the magnitude of a vector like that that has 2 orthogonal components, you square the first and then square the second, add them together and square, then take the square root. If you'll notice, sine squared plus cosine squared, square root of is 1. You with me? They are 1 by definition. Magnitude, and this is the relative unit vector direction. Do y'all follow me? So if I take this and I put it in here, I'll do it one time. Now I get, I'm going to do something else. I hope you appreciate this. If I take a look at this when I take A cross E, the only thing that I need to know about this is AY. All that stuff here is a scalar I can pull out in front. And I'll do that. That means I have E naught incident over a to 1, that'll be strict real, times e to the minus j, and this would be beta times x times sine of theta incident plus z cosine of theta incident. And then I have the unit, these are all the scalar terms I'm pulling out from. This unit vector, which is that. So I have sine of theta incident AX plus cosine of theta incident AZ. And that's crossed into AY. I hope you appreciate, I'm just trying to get this thing in a form that's easily for you to digest. With me? Take a look at that for a second. It's in your book. I'm trying to do this in a way that I would want it taught to me. Now, here's the deal. I can just modify this slightly. Y'all agree with that? That would be 1 over eta, the unit vector and direction of propagation cross D will give you H, right? Y'all with me, class? So, what actually happens here? Just look at this. I got AX, right? Crossed in AY is AZ. Yeah. So I'm going to do this. I'm going to sort of cheat. AZ, right? And then I have what? AZ crossed into AY, which is minus AX. And if you look in the book, you'll see this is what he has. What page is it on?
361.
All right, so that would be the H field associated with that E field, okay? Now, in the past, I do this for all three quantities. It's spent a lot of time. I'm just going to say this. This field in this direction coming this way and this wave here are basically just scaled versions of each other. Or this wave will have eta 2, or excuse me, eta 2 and beta 2, all right? And it will have the cosine and sine of theta transmitted. And the relationships in E and H will be the same. So I'm going to put the transmitted field right below. And these are in your book, but the transmitted E field will have E naught transmitted times e to the minus j. Here it would be beta 2 times x, and then it would be the sine of theta transmitted plus z cosine of theta transmitted, and it would be in the a y direction, and the H field transmitted would be some E naught incident, transmitted, pardon, over eta 2 times e to the minus j beta 2 times x sine of theta transmitted plus z cosine of theta transmitted. And then it would be times that business there, which is going to be sine of theta incident AZ minus cosine theta incident AX. Scam likely. Y'all get those? Tell you one thing, just off the cuff here. So I bought a car in 2010, a Hyundai Veracruz, right? Somehow they know that my policy of any parts go wrong is expired. It expires in 6 years, all right? So they have been trying to contact me by mail, by phone, no matter what I do to tell them, I don't want to be contacted. Tell them I sold the car. Tell them anything. It doesn't matter. They still contact and call, and I block their numbers, and it is like a most irritating thing. I see why people get a different cell number, but my wife did that. She had a different area code when she moved here and got married. And she just recently did this thinking it would eliminate the scam calls. Now you know what happens. She gets calls for the guy's number that had that before that number. And it just nonstop. So you can't beat these people unless. I have one thing that I'm about ready to invoke, and that is that block everything from numbers you don't know. In other words, if it isn't in your memory, block it. I'm about to do that. The only reason I don't is because a lot of times students and stuff like this, people want to contact me and I give them my number and I'm thinking, oh God. Now there's one other workaround. Now there's probably more than one. But there's a thing called Google Voice. All right, Google Voice is a godsend because if you use that number, the scammers are getting smarter. They realize that's a Google Voice number, and it's probably something you're never going to check. So they more or less, like I use this when I call car dealers, because they're going to keep calling you forever. And you can do that. I haven't done that on my phone. But then with Google Voice, you can't just pick up the phone and call. You got to activate that Google Voice thing, and then you can call. So there's more work. Anybody else got a solution for this? Anybody? What?
I don't know. I just have to live with it. I don't know.
Well, I'll tell you. The person that solves this, there's two things that if they solve, they'll be billionaires. That's one. The second is a way to mute commercials anytime they appear on TV during football games. Just mute it, all right? You don't even have to take it off. And if you can take it off more, that thing would sell like crazy, but you'd probably get sued by everybody and his brother. I mean, over there in the advertising world, because then it renders them useless. All right, so that's the transmitted field. Back to the real world. Now, there's a reflected field. This is the important one. I want to make sure you see. Listen. I'm going to try to put that reflected field right here. I wish I had the physics 3 boards bit. Y'all have this right here? I'm going to just give myself a little more room. So the reflected field, hear me here, the TE wave, E reflected will have some E naught reflection. That's just the scalar value. Then it's going to be at E to the plus J beta 1. Or no, you can put E to the minus J beta 1. That's how Dr. Wentworth does it. And then it will still have the X cosine of theta reflected, but then it'll be minus Z times the sine of theta reflected, minus Z times the cosine of theta reflected, AY. Now, you see what I've done there? I know the reflected wave is moving in the minus Z direction, right? So that's why I put that minus sign there. Y'all follow me on that? It's still moving the X positive X, right? It's still going this way, positive X, but it's the Z direction. That's E. Here, the unit vector changes too, because the unit vector on this one, for the reflected wave, will be equal to, it'll still have the sine of theta incident AX, but it will be minus the cosine theta incident AZ. Y'all with me on that? Now it's because it's going in the minus direction. Y'all with me? Now when you go ahead and get the H field, again, H reflected would be equal to 1 over eta 1, the unit vector and direction of propagation crossed into E reflected. Now you're going to get E naught reflected. That's just the magnitude divided by eta 1. And then it's going to be times E to the minus J beta 1 X times the sine of theta incident minus Z cosine of theta incident, reflected, pardon me. They're the same. This should be reflected angle here technically. And it would be in the AY direction. Oh, I'm sorry, not AY. It would be, then when you do the cross products, here's what you get. You're going to have X times the sine of theta reflected, AX times AX, hold on. No, I'm sorry, it's going to be cosine of theta reflected AX plus sine of theta reflected AZ. Take a look at that in your book. They're both plus. You see it? I'm not sure where that is, but it'll be cosine of theta X. There are cosine of theta reflected AX plus sine of theta reflected AZ. Y'all see that, class? Mm-hmm. Now, I don't ask proofs in this class, and I won't ask you to memorize some of this stuff, but you have to be aware of this to really understand how to do some problems. All right, all that's well and good. I've got transmitted and reflected E fields in both I've got the reflected, I've got the incident, got the transmitted. So now what we want to do is remember what the reflection coefficient was for the normal incident. It was just a relationship between the magnitude of the reflected wave and the magnitude of the incident wave, right? Same deal here. It's always going to be magnitude of E fields. And I'm going to have to erase this to do this. So now we're going to get the reflection and transmission coefficient. And transmission coefficients. In Dr. Wentworth's book, he does not break this out and state it, really boldly. I like to do that. Send me an email and I'll send you something about this that'll really, you can paste it in your book. It's useful. So now when we talk about reflection and transmission coefficients. All right, well, the reflection coefficient, if you remember, this is a reflection coefficient. That's just a relationship between the reflected electric field and the incident electric field, right? All right, here's how we do it. At the boundary, so at boundary, the tangent electric field in region 1 is equal to the tangent electric field in region 2. Do y'all agree with that? That E tan1 is E tan2, the tangent values, and H tan1 is equal to H tan2. Now when I say tangent, here's what it is in a simple sense. If I take this and I look at the tangent component on there, it's simply the shadow it would cast there if light was shining straight down on it. So it's really this times the cosine. Now, if I've got something like this, the tangent component is 0. If I have something like this, the tangent component would be all of it, whatever the length is, right? When I take a look at tangent component of the E field on this side, if you remember what I had there, E field was sticking out, right? So on this side, I would have an incident and a reflected field that would coalesce at this point because Z would be 0, wouldn't it? Right, at Z equals 0, take a look at this. You can make X 0 too. This whole thing just goes to 1. It's E to the 0 is 1. You can make Z equals 0. It's true everywhere, but it's true specifically there. So that means that E naught incident, this is at the boundary, plus E naught reflected, this would be for one ray that we're tracing of this thing, would be equal to E naught transmitted. Now, Dr. Wentworth's book has this, if you look. Y'all agree with that, class? That's for sure. And, I'm sorry, I erased part of that. The other thing has to be that H10 in region 1 has to be H10 in region 2, right? Correct, class? All right, here's where it gets a little sticky. I erased some of that. I still got the reflected field. I don't think I have the transmitted incident. When I look at that drawing, I had this is the Z direction. This is media 1 and 2. And if you remember, I had a wave coming in this direction, and I had the E field out. I had the H field drawn like this, right? Here, I had E field out, H field drawn like this, and here I had E field coming out, and I had H field like this, right? All right, the tangent component of the H field would be what? Would actually be the X component. You all see this? Because this is the Z axis, this would be the X axis. So the tangent between these two regions would be the X component of the H field. Do you all see that? How many do? You all with me? Sit. So I'm gonna do it. Well, I'd like to keep some of this, but if we see it's the X component, what do you see right here? Just look at the reflected field. It's going to be the cosine here, right, times this mess is equal to plus the actual component of the H field that's incident in the X direction. You got to add those two together and set it equal to the transmitted component. Are you with me, class? This is how you do this. This is E tan 1 is E tan, or I mean H tan 1 is H tan 2. So when I do that, I'm going to try to do it here. I have for the, and here's what I'm going to do to make my life easy. I'm going to let X equal to Z equal to 0. That way I can get rid of this exponential stuff. Y'all with me? It's true always, so it's true there. And that means that I have E naught reflected over A to 1 cosine of theta reflected. So I have E naught reflected times or over A to 1, and then it's times cosine of theta reflected, right? And then if you look at the incident field, this is the AX version, you're going to have plus E naught incident over A to 1 times cosine of theta incident equal to E naught transmitted over A to 2 times cosine of theta transmitted. And this would be the AX component. Do you see this in your book, by the way? I don't know exactly what page this would be on, but I think he just puts it all together. He doesn't even do that, does he?
No, I don't see it.
The E field's adding up around 363.
Yeah, that's the fine theta reflected as theta transmitted, but what I'm doing here, I don't see. He does do the final version. So anyway, when I do this right here, I'm going to make the claim, you can do this proof, because this has to be true everywhere, the incident reflected angle will be the same, and it's actually done here. If that's the incident E field, and I take a look at this plus the reflected equal the transmitted everywhere, if you make Z equal 0 at that surface, you find that beta 1 times sine theta incident has to be beta 2 sine theta transmitted. And also beta 1 sine theta incident has to be equal to beta 1 sine theta reflected. So I don't even mess with this. Angle of incidence is equal to angle of reflection. Can you all follow me on that? It kind of makes sense. Now, from here, by the way, I really want to get what? I want to get this relationship. So how do I get this relationship? Okay, here's how. I say the E naught transmitted is E naught incident plus E naught reflected. So I just replaced it down here. Now just watch. I'm going to divide this by 82. And now it's going to be E naught incident plus E naught reflected. Now you all see what I've done. I just replaced the E naught transmitted there by those two. It has to be the same, right? They have to be equal. And then what I'm going to do is divide everything by E naught incident. Are you with me? You don't need to know this exactly, just appreciate what I'm doing. When I divide by E naught incident, then I get my reflection coefficient's definition here, right? That's reflection coefficient, it's gamma R. This goes to just 1. This goes to 1, and this is the reflection coefficient. Are you with me? Right? Because reflection coefficient is reflected over incident. Then I got to rearrange everything, right? And solve it. When you go through and do that, I'm going to just, in the past I used to do this, but he has it in his book, and I'm going to show you something. When you do this, you get the reflection coefficient. You can take that to the other side, but you get the reflection coefficient. E naught, or gamma reflection is equal to, and I'm just going to give you a tip. Remember before, it was always the impedance you're going into minus the impedance you came from, right? Over the impedance you're going into plus the impedance you came from, right? I've done this many, many times. I can tell you that coefficient will be the cosine of theta. They call it cosine of theta transmitted. Or theta, or I'm sorry, cosine of theta incident. This is going to be cosine of theta transmitted. And I'm going to say this. He does use eta, right? Yeah. And this is going to be just the sum of the two, cosine of theta incident plus eta 1 cosine of theta transmitted. You'll have this in the book. This is a reflection coefficient, but he won't have this symbol yet. And this is E naught reflected over E naught incident. This is the important takeaway from this. Then you're going to have the transmission coefficient. And the symbol for transmission coefficient is tau. Now remember before, transmission coefficient was 2 eta 2 over eta 2 plus eta 1. I always put that down first in my mind. Well, I know the weight up here is going to be cosine of theta incident. Down here, it's going to be eta 2 cosine of theta incident plus eta 1 times cosine of theta transmitted, or theta 2. Are you with me? Now, this should, if I've done this right, when the angle goes to 0, right, the transmitted angle will be 0 also. But when the angle goes to 0, this should boil down to be that of normal incidence. And in fact, when the angle theta incident is equal to theta reflected and happens to be theta transmitted is 0, you have eta 2 minus eta 1 over eta 2 plus eta 1. It works, right? And the second thing is, when you talk about normal incidence, the transmission coefficient is 2 eta 2 over eta 2 plus eta 1. And in fact, that works too. That's a check, a mental check, right? So in your book, do you see this in your book? I'm looking for it.
That what you just wrote down is.
This is 6.133 and 6.134 on page 364. But he doesn't break out the reflection coefficient the way I did. I like it broken out, and this is for the TE mode. So what he'll do is have a little capital TE to remind himself. That's it, really. That's what we do. And of course, if the regions are the same, I've got to do one other thing to show you This is really called a phase matching condition, and we get something called Snell's law from it. All right, so I'm going to just do this over here. You've heard of Snell's law, right? So if you just look at the E field, when you had you had E naught incident, right? And then it was times e to the minus j beta 1 x, I'm going to let z equal 0, x times the sine of beta incident. This would be in the AY direction, by the way. So the whole thing is going to be in the AY direction. I'll do that right here. We have that. Then it's plus E naught reflected times times E to the minus J beta 1 x sine of theta reflected again, this is just at the boundary. This is going to be at z equals 0. It has to be equal to E naught transmitted times e to the minus j beta 2 x times sine of theta transmitted. That has to be true everywhere for all values of x, right? I mean, that's just from the tangent field condition. E tan 1 is E tan 2. Now, the only way that's going to be true for all values of x, right, is if this quantity always has the same phase as this quantity, and always has the same phase as this quantity. Otherwise, if beta 1 sine theta incident, if that scalar value is larger than either of these two, the beta 1 sine theta reflected or beta 2 sine theta transmitted, as I change values of x, the angle changes and it can't be equal. Do y'all follow me? It can't be equal. So that gives us Snell's law that beta 1, this is Snell's law, times the sine of theta incident has to be equal to beta 1 times the sine of theta reflected, which means theta incident, theta reflected are the same, also has to be equal to beta 2 times the sine of theta transmitted. That's how they get Snell's law. And the form of Snell's law that's most common in electromagnetics is this one. This is Snell's law. You can write this down. This is important. When you have Snell's law, it says that beta 1 times the sine of the incident angle is equal to beta 2 times the sine of the transmitted angle. Now, this is a lossless medium. So if you look at beta 1, that would be omega times square root of mu naught, epsilon, mu naught times epsilon naught, times the square root of mu relative epsilon relative for region 1. That would be times the sine of theta incident is equal to, and here we put it beta. Beta is just omega times square root of mu epsilon. So I'm going to break out mu naught epsilon naught times square root of mu relative epsilon relative times the sine of theta transmitted. Are you with me, class? Now, here's where it gets interesting. This is for a lossless material. You all see how much stuff cancels on either side? Does everybody see this? Omega cancels for starters, right? So cancel omega. After that, the speed of light over 1 cancels. 1 the square root of mu naught epsilon naught. Now I have this. That's Snell's law. But what's commonly seen when you talk about Snell's law is they'll use it for non-magnetic materials. And for non-magnetic materials, mu relative equals 1. And that means I have the square root of epsilon relative 1 times the sine theta incident equals the square root of epsilon relative 2 times the sine of theta transmitted. Does anybody remember, I don't know if you do or not, from physics or from anywhere, what the square root of epsilon relative was referred to as? Mamma mia. Anybody? It's a common term, you use it in physics, you probably had it in high school, maybe grade school. It's called the index of refraction. Index of refraction, which is a function of frequency. So when we talk about and you can write this down, the index of refraction and that symbol is just small n. I don't like it because it looks like eta. All right, so I don't like that. But it's n, and it's equal to the square root of epsilon relative to the medium. And the common form is just intrinsic impedance of region 1 times sine of theta incident is intrinsic impedance of region 2 sine of theta transmitted. Now, why is that important? Well, has anybody ever thrown something in water or shot an arrow in water trying to hit a fish or anything? What does light do? It bends, right? So when we talk about having air here, and then water here, water has an epsilon relative that's much greater than 1. It is a function of the frequency you're at, quite a function actually. But at moderate, well, I say moderate, at frequencies of like 10 to the 6th, 10 to the 7th in water, and you can even go a lot higher than that, but I'm just going to say this, epsilon relative for water, you can Google it and see, is about 81 over a fairly wide band of frequencies. Now, anytime you have epsilon relative, you go real high frequency, it tends to be 1. Same with mu relative. When you go to super high frequencies, the value of both go to about 1. Why? Because the molecules can't move fast enough because of their inertia. So the effect of polarization or magnetic moment is unaffected. It can't affect the wave if it's super high frequency. And what is that? Well, it depends on the material. But if epsilon relative is 81, here's the kind of problem I can give you. And I'm having a wave come in here, right? Let's say the incident wave is coming in at 45 degrees. These people that go, they go boat, they use an archery for fishing with a bow, bow fishing. They'll aim at 45 degrees and even less. That might be 55, 65 degrees. But when they're looking at that fish, it's not in the line of sight. What actually happens is this light is going to bend, and this angle is going to be much less. That's the transmitted angle. Let's figure out how much it bends if we have water for this problem. So here's the bow hunter up here. He's looking at a fish. The angle here is 45 degrees. All right, the angle is always measured from the normal to. All right, so what's the transmitted angle? Let's do the math on this. All right, beta 1, well, air has an epsilon relative. You can just use this one of 1. So when I have sine of theta incident is equal to, well, I made it 81. It is 81 for some range of frequencies. Square root of 81 is 9 times the sine of theta transmitted, all right? I made the incident angle 45, right? What's the sine of 45 or sine of pi over 4? 1 over square root of 2. It's a very common thing, right? 1 over square root of 2. So I have 1 over the square root of 2 here. Then I divide it by 9, And that's equal to the sine of the transmitted angle. So what's the transmitted angle? Well, do the inverse sine of 1/9 divided by the square root of 2 and so on. You got your calculator? I like to, that way you got a real example. You're gonna see it ain't much. 1, 2, 3 degrees, 5 degrees. It's a lot less.
0.07.
What is it?
0.07.
No, put it in degrees, not radians. Sorry.
Yeah, 4.5.
4.5 degrees. All right. Anybody confirm that? All right. That's just about straight down, isn't it? Now look, if you're looking at a fish and his apparent position is here, he's actually down here. And if this range is 3 foot, right? It would be 3 foot that way, so you got to shoot way under. There's all these problems you can do calculating how much adjustment you need. But remember this, that if you're trying to hit something in the water, the thing basically bends almost straight down. Just assume whatever distance you're looking at there is straight down. Where would you shoot? And you'll hit it then. Right? Because if you look at an arrow, or any kind of a long object, a straight long object, and you put it in the water, you'll see it bend like this. I don't know if you've ever done that, but it will bend like crazy. It's something to keep in mind. And how we know that and why it happens is from fundamental physics, and we just match boundary conditions. All right, so that's TE. Now we do TM, transverse magnetic. This one has an interesting effect. It's called Brewster's angle. How many remember Brewster's angle from physics? Anybody? It's the angle at which you get total transmission into a second medium, even though the impedances are different. Which kind of blows people away. You get no reflection. Brewster's angle, there's a lot of things used for this. You wear polarized sunglasses, right?
Mm-hmm.
All right, do you know what polarized sunglasses really do? Well, light itself is randomly polarized from the sun. So when it strikes the surface and you get that reflection, it has to do with the reflection being from the I better draw this, but the perpendicular component of the electric field. Anyway, it has to do with the type of photons. And if you block those, and that's what your lens does, if you block the type of scattering from the wave, the actual TE, I think it's going to be TE, we'll find out, wave. And you can do this very easily with slits, by the way, very thin slits. Then the other one, the TM wave, penetrates, all right? It gets tremendous penetration into the area, and you get very little glare. I'll try to, that's not a very good explanation, but I'll try to elaborate. Really what it amounts to is the type of field that you see is the kind that doesn't cause any kind of surface reflection. In other words, you see better. All right, so what happens with TM? This is TM, transverse magnetic. The word transverse means perpendicular to. So here, if we have region 1 and region 2, and you have, this is the z-axis and this is the x-axis, now, if we take a look at a wave coming in at some angle, theta incident, this is the direction of propagation. Now, we're going to assume the H field is sticking out of the board. All right? With me?
Mm-hmm.
And I want to be consistent with Wentworth's notations. Dr. Wentworth has this book, and some of this stuff is not, I think, the most common way to do it. But this is on page 366. Yeah, Yeah, he's got his H field sticking out. And if you look at this, if the H field is coming out, I know that E cross H is the direction of propagation, therefore the E field is in this direction. It has both X and Z components. The H field only has Y components. Do y'all follow me on this? Now, in the same manner, you're also going to have a transmitted field here that will have a H transmitted here and a E field transmitted here. It'll have this form. And you're going to have a reflected field. Here's the thing that's interesting about this. Now, this is Wentworth's convention, but it is common. You're going to assume the H field here flips directions. Take a look at that in your book. He's going to have H going into the board, all right? And I know E cross H is direction of propagation, so the E field has to be up here. The reflected field is going to be in this direction. Y'all see that? Take a look at his book, all right? So he flips the direction, the H field. And the reason is he wants the E field. Basically, he defines it as such. Now, the truth is, well, what if the H field actually has a value that's coming out? Then this value will be negative. That's the deal. But these are the assumed directions. So when you get this, as before, and he does this, you're going to assume, and the way he does it is, you're going to assume an H field. I'm just trying to make sure he does this. Yeah, he does it. Here's what he does. For the incident field, he's going to have H incident, since it's perpendicular, is going to be equal to E naught incident over eta 1. He's going to keep this ratio the same. Now he's going to take it times e to the minus j. This will be the same as before. Beta 1 x times the sine of theta incident plus z cosine of theta incident. Right there. And this will be in the a y direction. It's coming out of the board. Y is out of the board. So from that, I can get E, right? E reflect, or E incident, pardon me. E incident, which would be, do you remember what the formula was for plane? We're assuming it's plane wave. How you would get it without doing a curl. We could take the curl of H, right? And set it equal to J omega epsilon 1 times E, right? But you remember the trick, right? Minus the intrinsic impedance in region 1, right? Times the unit vector in the direction of propagation crossed in to the H. Well, I can go ahead and do this. All right, we can get a vector. Unit vector in the direction of propagation is going to be what? Well, it's going to be sine theta incident times AX plus cosine theta incident times AZ, right? And we can take that and do the cross product. Now he does this for us. I'm getting a little short on time. And he has this shown on page 366. It's equation 6.138, and it'll have a cosine of theta incident AX minus a sine of theta incident AZ. And then what he'll have here, in multiplying these, will just be E naught incident times e to the minus j beta 1 x times the sine of theta incident plus z times cosine of theta incident. And can you also, do you see that in the book? Now here's the thing. He has E naught times cosine theta incident. You'd have to multiply to get the weight on the value of AX, the EX component. By the same token, you have to multiply sine of theta incident times E naught incident to get the weight on the value of AZ. But he does this for a reason, because this ratio of E over eta being H and magnitude is used all the time. That's the reason he does it. All right, in terms of just magnitude. So that's going to be the incident E field. Now, I'm going to just say this and cut to the chase here. Y'all see for the transmitted version, same as this, only then it's E naught transmitted. This is eta 2, this is beta 2, this is sine of theta transmitted, this is cosine of theta transmitted. Y'all with me? Same here for the E field. Now this is cosine of theta transmitted, minus, or AX minus sine of theta transmitted, E naught transmitted, e to the minus j beta 1, or beta 2, pardon me, times x sine of theta transmitted plus z cosine of theta transmitted. You with me on this, class?
Yeah.
The difference is the reflected field. For the reflected field, this will have a minus sign here, all right? It would be minus z, remember that? And this will have a negative sign as well, because he's assuming it goes in. And this would be E naught reflected. This right here will be the same, except that on this one, they're both negative, or excuse me, they're both positive. This would become positive. If you look there, the E field has both a positive Z and X component for the reflected field. So this would become positive, the reflected, and this would become negative. Now, it's in your book. I don't expect you to recreate this. I'm not going to ask you to prove this. Just be aware of how it's done. Then they match boundary conditions. They say at the region Z equals 0, right there, E tan 1 is E tan 2, H tan 1 is H tan 2. Do you all follow me on that? When you do that, now you get the reflection transmission coefficients for TM wave. That's what I'm going to write down. If you're curious, go prove it to yourself. Every once in a while, I get students who are very good with mathematics and physics, and they enjoy doing this. You can go ahead and just straight, clean sheet of paper without looking at anything, see if you can prove this. And I mean, when you go for your PhD and stuff, you do this all the time because it's something they assume you know how to do without even thinking, and you should. But you guys, I don't expect that. I just expect you to be aware of what you need to do if you need to do it. So, when I get down and I get the reflection coefficient for the TM wave, here it'll always have eta 2, it will always have eta 1, then it will have eta 2, it's going to be a minus sign, it'll be a plus eta 1. I know that's always going to be the way it is. Now the weights, before it was cosine of theta incident. Take a look in your book. Here it's going to be cosine of theta transmitted. Take a look. Minus N1, and it's going to be cosine of theta incident, or theta 1. And here it's going to be N2 cosine of theta transmitted plus eta 1 cosine of theta incident. And y'all see that this is equation 6.141. So what actually transposed? Instead of incident, it's transmitted angle here. Instead of incident, instead of transmitted, it's incident. Y'all follow me on this, class? Mm-hmm. That's the difference. However, what your gut tells you is, well, that means for the transmission coefficient for TM, it should be equal to 1 plus reflection coefficient for TM. That's not true. All right? It's not true. All right? The reason is the reflection coefficient has to do with the tangent, has to do with the ratio of electric fields to transmit and not magnetic fields. It would work if it was magnetic fields. So here, what you have to do is say the transmission coefficient, TM. Now, you know from before that you're always going to have a 2 eta 2 up top, and you're always going to have an eta 2 plus an eta 1, right? You know what I'm doing there. That's normal incidence. I know that. But take a look in your book. Now, this becomes cosine of theta incident, doesn't it, on top? Take a look there. Now it's going to become eta 2 cosine of theta incident. And downstairs, this is going to be cosine of theta transmitted plus N1 cosine of theta incident. And and this is on equation 6.142. And then he has in 6.4 or 143 the relationship between the transmission and reflection coefficient. You'll notice they're not equal. It's multiplied by a cosine of theta incident over a cosine of theta transmitted. Y'all see that? All right. So remember that. This is the trick right here. All right, the reflection coefficient is key. Now, that said, if I've got the incident field and I want the reflected field, I find that coefficient multiplied, I have the reflected. Want the transmitted field, I find that coefficient multiplied, right? That's what I do. There's a point that's very interesting, and that is where the actual reflection coefficient here goes to 1, and if you look, it's called Brewster's angle. And he says on page 367, for TM polarizations, there exists an incident angle at which the wave is transmitted to the second medium. This is known as Brewster's angle. And it can be found by setting equation, really the reflection coefficient equal to 0. All right, so here's what happens. This is the reflection coefficient, right? When we take a look at Brewster's angle, I'm going to do it here. So, total transmission we want the reflection coefficient for the TM wave to be 0. That should make sense. If nothing's reflected, it's got to be transmitted. All right, what you're going to find though, the transmission coefficient doesn't equal 1. You know why? Because the transmission coefficient has to do with the magnetic, or has to do with the ratio of E naught transmitted to E naught incident. And remember, the E fields transmitted are not at the same angle as the E fields incident. Now the power, this is an interesting thing, the normal power into the region is always the same on one side or the other. So the power flowing normal to the region will be equal to the power flowing this way. However, what happens is the power flowing in medium 1 is at a different angle than the power flowing in medium 2. The actual perpendicular components will be the same. All right, that's the important thing. And for this, the reflection coefficient is 0. Well, what does that amount to? Take a look here. That means that this is equal to that, right? So when we say that therefore eta 2, and it's going to be times cosine of theta transmitted is equal to eta 1 times cosine of theta incident. Y'all with me? This is how you calculate Brewster's angle. Now, this is just sort of a little mathematical, it takes a little time to do this, but what we want to do is find out the incident angle, all right? We want to know Brewster's angle for any material, all right? We want to know when this is true. And Brewster's angle has to do with the incident electric field's angle. So you put a little b here, all right? With me? Mm-hmm. Then you can mess with this. You can take a look at this. I know that beta 1 times sine of theta incident is beta 2 times sine of theta transmitted, right? I bet you know what I'm going to do. It's a little trick. I want to get everything in terms of material properties, not theta transmitted. Well, when I do that, I find out something. Really, I got a cosine of theta transmitted there, right? Mm-hmm. And I know what I'm gonna have as the incident angle there is the Brewster's angle, right? Right? So when I go ahead and I'm gonna go ahead and square, I'm gonna do it this way, square both sides, so I have beta 1 squared sine squared of theta Brewster's is equal to beta 2 squared times sine theta 2 squared. And then I can say, well, I have that. I'm after this, so theta 2 would be theta transmitted right there. And I can say that this is equal to beta 2 squared times 1 minus cosine squared of theta transmitted. You all realize, follow me on that? 1 cosine squared plus sine squared is 1. If I want to know, if I've got sine squared, I can replace it by 1 minus cosine squared of that angle, right? Now, after that, I'm going to take this and I'm going to take this to the other side, and it would be a minus, and then I got to get rid of that minus sign. So then I have beta 1 squared, or beta 2, pardon me, squared, minus beta 1 squared times the sine squared of theta Brewster's is equal to beta 2 times cosine, beta 2 squared cosine squared of theta transmitted. Now here's the deal. I can divide this by beta 2 squared. I'm just going to do it here. And then take the square root. And now I have cosine. I'm trying to do this kind of fast because I'm just about out of time. Y'all with me?
Mm-hmm.
Now I can take that cosine of theta t right here and substitute it in to this, what did I have right here? I can substitute this cosine equation right in here, and then I've got a sine squared of the Brewster angle and a cosine squared, right? I can manipulate that further, and I can get the tangent, and that's what Dr. Wentworth's book does. And actually does it in terms of a sine. He breaks it in terms of sines, but he's doing what I'm doing. And he finds that the Brewster's angle is given in 6.146. That's the general form. It's just by manipulation of Snell's law. That, and if you turn the page on equation 6.147, I'd highlight that because that one is assuming it's non-magnetic. And therefore, you can get something that's just the ratio 1 over 1 plus epsilon relative epsilon 2 square root would be the inverse of that would be the Brewster's angle. With me? I think what time do you guys have?
2:29.
29? I've got a minute. All right, I wanted to go through that. Now, a lot of stuff with oblique incidents. This is the last part of chapter 6. People get a little irritated, they get concerned, and I'll tell you, there's more to this. I may talk next time a little bit more about polarization filters and why polarization glasses work, but fundamentally is that they only permit certain polarizations to get through. They have thin slits, electric fields having that component get through. Now, if you think about Brewster's angle, we assume that the H field would be out. If you had like air and then water here, this would be like media 1, media 2. The H field was out, the E field was in the plane, right? That's propagating. So if I had an E field like that, there would be a transmitted field with an E field like this. But with Brewster's angle, we know at the Brewster's angle, everything's transmitted, right? Well, water has that. So that means the reflected field would be 0, correct? And that's what polarization sunglasses do. They only permit light with a vertical electric field polarization to come through. So, and this is something you should try. If you take two lenses that are polarized, and you put them over each other and turn them, they'll go from something you can see through to complete black. Does anybody ever do that? Does anybody here have polarization sunglasses? You got a pair, does anybody else? I'll show you right now. Because this will keep you, it'll keep
You
stay,
got a
it'll
pair
stay.
with them? Oh, anyone's got a pair with them right now?
You have polarization?
Oh, not with it. So,
Anybody? I don't want you to break your glasses, and I don't. Guys, next time bring your glasses, somebody else bring them, because I might forget. But if you take the two lenses over each other and turn them, it'll go completely black at a certain point. Now, when you're looking with polarization glasses and you're looking around water, you can see underwater pretty good. Has anybody else noticed that?
Mm-hmm.
You'll be able to. But if you take those glasses and turn your head like this, you'll go blind. You'll get this tremendous amount of glare. Because what they're doing is it's permitting only light with vertical polarization. And the neat thing is the light you're getting is not directly, there is a component, all right, but it's not the light that's going to be, it gets rid of that horizontal component that's the glare. But you got to try this. Remember what I told you, find some polarization glasses, just go to a store and grab a couple pairs. Do this, those are polarized. Because if they say they're polarized and they don't do that, don't buy them. All right. I'll see you next time. I'm tired today. I've been tired the last couple of lectures. But I'll get over it.